A wheat kernel is going to be 8 to 15% protein. And of the protein in that wheat kernel, 85 to 90% is going to be gluten. Now, gluten is not really one thing. It's really more of a concept. Gluten is really a network of lots of different types of proteins. And the two main categories of proteins in gluten are glutenin and gliadin. Proteins can take on two different personalities. They can be hydrophilic, which means they feel perfectly fine in water, or hydrophobic, which means they don't really like the water. And the proteins in dough are hydrophobic. That's why dough changes its structure so much when you just add water to it. And what happens is we have these proteins, they're hanging around and they're perfectly fine because there's no water, but then you introduce water to them. And when you introduce water to them, it's like they don't like it. And so they tend to kind of huddle together and become closer to one another. So it's going to change its shape considerably. It's kind of like if you and your friends are out in a safe place, you're hanging out at a natural distance from each other. But then if something scary happens, maybe you hear a loud explosion, you tend to huddle together. Well, that's the same thing these proteins are doing when you add water to the flour. That's why you're able to take very strong proteins and just give them a very different shape. When we knead dough, we're shaping the dough. And really what we're doing is we're shaping the proteins in the dough. We're shaping the glutenin, and we're shaping the gliadin. Now we need to understand a little bit about proteins to understand how kneading works. And so we're going to be using these colored yarns as a metaphor for our proteins. A protein is just a shape that contains a bunch of amino acids that are hooked together. And the neat thing about proteins, they can come in all different types of shapes. The glutenin tends to be long chains of proteins, whereas the gliadin tends to be clumpy. They clump together and form something that's resembling balls. And with the proteins, when you're kneading dough and the gluten, what we call, develops, these proteins are interacting with each other to make different shapes. And there are two main types of interactions between different proteins. One is a weak interaction. And so notice in this model of glutenin, there's different colors in this yarn. And likewise, on the protein chain, they'll, at different segments, at different parts of the amino acids, there'll be positive and negative charges on it. That means when you put two glutenins closer together, some parts of the positive chain on one will attract the negative chain of the other. Now, they're not forming a bond, they're just being attracted to each other, and they're going to be on one chain of glutenin, they'll be attracted to different parts of it. So glutenin is going to do some weird things. They're going to make these little loops like this, and they're going to connect with other glutenin strands. You can think about these weak interactions kind of like water, H2O. And that H2O molecule, on one side it has a negative charge, and on the other side it has a positive charge. And that's why the water molecules, they attract, they're sticky, they stay close to each other, but they also spread out. It's negative and positive. And that's what these weak interactions are like. And remember we said the gliadin tends to form in little balls, but they're also going to have these weak interactions. And when you put a bunch of gliadin together, they're going to tend to form something like a matrix. And we have lots of different sizes here for the gliadin because there's no just one gliadin. Gliadin is just a class of proteins. In addition to weak interactions, we have strong interactions between proteins. And this occurs, and of course we call it strong because the bonds are much stronger. And this usually occurs when different proteins start to share an electron. They get a covalent bond. And so you'll have this where you can have strands of glutenin, and they may form a disulfide bond here where they're sharing an electron, and they create a bond there and it's strong. But you also have gliatin in here. Gliatin can come in and form a strong disulfide bond with the glutenin as well. And so when you mix all of these proteins together, and remember gluten is just a bunch of gliatin and glutenin together, they're going to also form a lot of these strong disulfide bonds. And so throughout here we have weak interactions and we have strong interactions, and we can manipulate those interactions to create the perfect dough, one that has a nice shape but can also expand but can also trap carbon dioxide. Okay, remember, gluten contains glutenin and gliatin. And when we knead dough, we're stretching the dough out, stretching it out repeatedly. And let me show you what would happen in that dough, in these proteins, if the dough only contained glutenin and didn't contain gliatin. So let's look here. We have these two strands of glutenin here, and it'll have a shape like this. There'll be some places where they have a weak bond, and then we'll have little loops like this, and this is where we have weak bonds within the same chain. Now once we knead a dough, we're pressing the dough, we're stretching it, and we'll be stretching out these glutenins. And what will happen is this weak bond that caused these places right here to attract each other, we're going to break those. And so we're stretching out the glutenin, and then it's going to form weak bonds like this. They'll be like parallel. Now when you do this, you've stretched it out as far as you can go. And so you don't have that elasticity. You don't have the push and then pull back. And there you won't have a good dough. So it's very essential. The role of the gliatin here is that when we stretch these out, the gliatin is going to come in and let it form these little loops again. Okay, stop. Now I want to show you what happens when we knead dough and the dough has both glutenin and gliatin together. So our dough is going to start off with a certain geometry, a certain arrangement of glutenin and gliatin. And this is when we mix the dough with water and yeast. And then we start to knead the dough. And when we knead the dough, we're stretching it. And when we stretch it, now remember, the glutenin and the gliatin, they've got weak bonds, but they also have very strong bonds, those disulfide bonds. When we stretch it, we're breaking those bonds. And so the gliatin comes loose from the glutenin. And once those bonds have broken, they can now form new bonds in a different pattern. So we've stretched it. And what's going to happen is the gliatin is going to form itself in that matrix pattern that it likes to do. And then the glutenin is going to be kind of weave itself all around the gliatin. And when you have that perfect arrangement that gives you that perfect dough, what happens is when you have the yeast in the dough and the yeast is eating the sugars and releasing carbon dioxide, the gas in the dough starts to expand. And the arrangement here is able to capture that gas. And so these proteins are going to expand somewhat. And it's the gliatin that allows it to expand. But then it's the glutenin that keeps it from expanding too much, because it's not going to want to break this chain. And so the CO2 is released. The gliatin allows it to expand. The glutenin keeps it from expanding too much. So when you're kneading a dough, The gliadin is like ball bearings that allows it to expand, and then the glutenin is what brings it back together. And you have the perfect dough when you have the perfect combination and arrangement of these glutenins and gliadins.